What if I told you the entire global supply of refined fuel relies on a single spinning machine? This is the heart of the refinery, the industrial turbine.
Welcome to the Deep Dive. Today, we decode the incredible engineering that powers modern oil processing plants, the intricate workings of gas and steam turbines.
Refineries are power-hungry giants. They demand consistent, massive energy to move, heat, and transform crude oil into usable products. Reciprocating engines are too slow and inefficient for this scale. We need reliability, high power density, and consistent torque. Enter the industrial turbine. These rotating machines convert thermal energy into mechanical work, driving the refinery's crucial compressors in generators. We primarily use two types: gas turbines for high power generation and steam turbines utilizing heat recovery for ultimate efficiency. Let's begin with the gas turbine cycle, often called the Brayton cycle. It's an elegant four-step process: intake, compression, combustion, and expansion.
Step 1. Intake. Air, the working fluid, is pulled in through an inlet filter system, crucial for protecting the delicate internal components.
Step 2. Compression. A huge axial flow compressor uses rows of blades to rapidly increase the pressure of the incoming air, sometimes by a factor of 40 or more. This high-pressure air is now ready for the furnace. Compressing the air efficiently is the single biggest determinant of turbine performance. Step 3. Combustion. The compressed air is mixed with fuel, often natural gas or refinery off-gases, in the combustor. This creates extreme heat, reaching temperatures exceeding 1500 degrees Celsius, far hotter than the metals can withstand unprotected. Special cooling techniques, like film cooling, are necessary. A thin layer of cooler air insulates the combustion chamber walls and turbine blades.
Step 4. Expansion. The superheated high-pressure gas rushes into the turbine section, spinning the rotor like a giant, powerful pinwheel.
The turbine section is where the magic happens. The energy conversion from thermal to mechanical power drives the shaft.
The first few stages of turbine blades extract the most power. These are the most stressed components in the entire plant.
The mechanical work produced is used for two things: driving the compressor, self-sustaining the cycle, and powering the external load.
The external load could be an electrical generator, providing the massive power grid needed for the refinery operation. Or, importantly, in a refinery, it could drive a crucial process compressor, like those in the catalytic reformer or hydrotreating units.
The efficiency of the gas turbine is linked to its compression ratio and the maximum firing temperature. Higher is always better, but harder to maintain.
Finally, the exhaust gases exit the system. While spent, they are still extremely hot, a massive amount of wasted energy if not recovered.
This waste heat is the bridge that connects the gas turbine to the next powerhouse we explore, the steam turbine.
Steam turbines leverage the Rankine cycle, creating mechanical power from expanding high-pressure steam. They are the workhorses of combined cycle efficiency.
In a refinery setting, this steam often comes from a heat recovery steam generator, or HRSG, utilizing the gas turbine exhaust.
Water is pressurized and pumped through the HRSG tubes, turning into superheated, high-pressure steam, sometimes exceeding 100 bar pressure.
This high-pressure steam is piped directly to the steam turbine, which structurally looks similar to the gas turbine, but operates very differently. Instead of combustion heat, the energy comes purely from the thermal potential of the pressurized steam. Steam turbines are typically multi-staged, designed to efficiently extract energy as the steam pressure drops across each stage.
We often see different pressure sections: high pressure, intermediate pressure, and low pressure sections, tailored for optimal extraction.
Crucially, steam turbines can also draw steam directly from refinery process units, like catalytic crackers, further maximizing resource utilization. The expansion process turns the rotor, creating mechanical work, which, like the gas turbine, can drive generators or large pumps. After expanding, the spent, low-pressure steam must be returned to liquid water to complete the cycle. This happens in the condenser.
Condensation. Massive condensers use cooling water, often from cooling towers, to quickly drop the steam temperature. Condensers operate under a deep vacuum, which significantly enhances the efficiency of the steam turbine cycle by maximizing the pressure differential. The resulting water, called condensate, is then pumped back to the HRSG or boiler, completing the closed-loop Rankine cycle.
But what about the steam used directly in processes, not just for power generation? Steam is essential for heating crude oil and distillation towers. The steam turbine helps balance the refinery's steam network. If excess steam is available, it's converted to electricity.
If demand exceeds supply, auxiliary boilers must kick in. The turbine system provides essential flexibility.
Controlling corrosion is paramount. High-purity deionized water is necessary, as contaminants can destroy the turbine blades and boiler tubes quickly. Without strict water chemistry, scaling and pitting would lead to catastrophic turbine failure and costly downtime.
Now let's combine them. The combined cycle gas turbine, or CCGT, achieves unparalleled efficiency by utilizing both cycles sequentially.
This integration is often called cogeneration or combined heat and power, CHP, in industrial contexts like refining.
The hot exhaust from the primary gas turbine becomes the fuel for the steam generation, achieving thermal efficiencies up to 60%.
Refinery turbines are often configured in simple or complex layouts, depending on space and utility needs.
The efficiency gain is critical. Every percentage point saved in energy translates to millions in operational cost savings annually.
The mechanical coupling requires sophisticated alignment. Misalignment, even by micron levels, can destroy high-speed bearings.
Specialized couplings, like diaphragm couplings, accommodate slight thermal expansion and minor misalignments during operation.
Starting up these massive machines is a carefully choreographed process, taking hours to ensure slow, even heating and thermal stabilization.
Ramping up too fast causes thermal stress, leading to blade cracks and eventual failure. Precision control is non-negotiable.
Modern refineries use advanced distributed control systems, or DCS, to manage these complex startups and shutdowns seamlessly.
Fuel flexibility is another huge benefit. Turbines can run on natural gas, fuel oil, and crucially, refinery off-gases, burning products that would otherwise be flared.
This ability to consume internally produced low-value gas makes the refinery almost self-sufficient in power generation, enhancing sustainability. Combustion controls must constantly adjust for varying gas composition, ensuring stable flame temperature and minimal nitrogen oxide (NOx) emissions.
Low emission targets demand precise air-fuel ratios. Too lean, and the flame blows out. Too rich, and emissions spike.
The massive size of these units also means huge inertia. They provide vital grid stability, absorbing temporary fluctuations in load.
Let's focus specifically on refinery applications. One key use is driving the massive process compressors found in hydrocracker and hydrotreating units.
These compressors handle huge volumes of hydrogen and hydrocarbon gases under intense pressure, critical for chemical transformation.
Turbine drives allow for variable speed operation, giving operators precise control over the throughput and reaction severity. The turbine's rotating speed can exceed 5,000 revolutions per minute, often requiring complex gearboxes to step down the speed for slower, heavier process equipment.
Another major role is powering the main circulation pumps that move crude oil and intermediate products between towers and tanks.
Reliability is crucial. If the pump driving the crude oil feed fails, the entire distillation column can shut down instantly. Many steam turbines are used for smaller, non-critical pumps, exhausting their low-pressure steam directly into the plant's utility header for heating purposes.
This cascading use of energy, from high-pressure steam for power down to low-pressure steam for heating, is the ultimate lesson in refinery efficiency.
In the event of a total power outage, called a black start, small auxiliary turbines or diesel generators must quickly restart the utility steam boilers.
This is essential to bring the main turbines back online, ensuring the refinery doesn't remain crippled for extended periods.
Turbine vibrations are meticulously monitored. Sensors track axial displacement and radial vibration to catch bearing wear early.
If vibration thresholds are exceeded, the system automatically triggers a protective trip, shutting down the unit to prevent catastrophic destruction.
The internal clearance between the spinning rotor and the stationary casing, the tip gap, is tiny, often measured in fractions of a millimeter.
If thermal expansion causes the blade tips to rub against the casing, a rub, the entire machine must be inspected immediately for damage.
This continuous monitoring turns the turbine into a living organism, constantly feeding data back to the centralized control system.
Maintenance is key. Large gas turbines require major inspections, called hot gas path inspections, every 24,000 to 32,000 firing hours.
These inspections involve removing and meticulously examining every single blade and vane that sees the hot combustion gases.
Predictive maintenance using AI models now analyzes acoustic data and temperature trends, often spotting subtle failures months in advance.
Mastering the turbine is mastering the refinery. It ensures high throughput, product quality, and uninterrupted global energy supply. From compressing air to condensing steam, these precision machines are arguably the most vital components in our modern industrial world.
Thank you for joining us on this technical journey. Don't forget to like and subscribe for more updates on cutting-edge industrial technology.